Okay, so last time we learned how to measure pressure. Pressure is relatively easy to do because we understand how to measure those kind of things. But gases are more than just pressure. There are actually several factors that influence gases. So pressure, of course, is one of them. But the temperature is, has something to do with how gases behave. In fact, it has a lot to do with it. The volume or the container size that the gas is in also matters, and the amount, okay, moles, which we call N in the gas laws, okay, that also is influencing the behavior of the gas. Now, we're going to be studying something called ideal gases, where we want something to have a linear relationship. So if we graph these out, we want to see a linear relationship between these different variables. However, you can't just go to do an experiment where you don't control things, okay? So in order to control things, many of these laws that we're about to study only two variables and hold all the rest constant, okay? So typically you'll have a typical experiment. You're going to hold two variables constant. In other words, you don't change the temperature, or you keep the same amount or something like that. And so you have two variables that never change. You change the temperature, for example. Okay, you change one of the variables and you measure the last variable, or the one you're interested in. Okay, so you kept two constant. Okay, so let's just say the volume and the amount. All right, then you, for example, change the temperature and you measure the pressure to see what happens when just the temperature is changed. All right, so there are several laws. I don't really expect you to know their names, but you definitely need to know what their relationships are. So Boyle's law is the first, and Boyle's law says basically that the pressure and the volume are related. So we're talking here about experiments between pressure and volume. All right, there's Charles's law. In that case, we're talking about temperature and volume. Okay, so in this case, we're holding N and temperature constant. Here, we're holding N and pressure constant. Okay, so these are how you set up these experiments to figure out how each one of these variables matters. In this case, in Avogadro's law, not an avocado, you look at N and temperature, meaning that you're going to keep pressure and volume constant. All right, we will come back to ideal gas laws later, okay? And at the end of this lesson, we're going to look at something called combined gas laws. All right, so we're going to look at how a reaction or a system changes if you do more than one change at a time. But we'll deal with that in a few minutes. All right, so Boyle's law. Boyle had this great apparatus. I heard this story. I have no idea whether it's true or not, but I heard a story that he had a big entryway in his English gentleman's manner, okay? And he had a staircase that spiraled around. And what he did was he had his big apparatus down at the bottom, and he ran up to the top of the steps and added his mercury or whatever he was working with at the top to check the value, to check the pressure and the volume. So he used the mercury for pressure, okay, and the volume is whatever is trapped inside of this tube. Now we use something called a J tube now, okay, and we don't have to run up and down stairs or whatever to make this work. It's much smaller than that, but in this case, we know what volume, all right, is in this end of the tube, in the J tube, all right, and we know what the pressure is going to be. In this case, we have a pressure change of delta H from here to here, and we calculate that up, and in this case it says that's 780 torr. All right, so now we're going to add some mercury in this case until we have halved the volume. This used to be 20 mils, and now it's 10 of gas in this trapped end. All right, and so we halve that volume, and we end up basically doubling the pressure. Okay, and so in this case, the pressure is proportional to the volume. Okay, in some way. All right, in some way. But is it directly proportional? And the answer is no. All right. When we graph this, here's pressure. All right, and here's volume. And so notice that we don't get a linear relationship. Now, we want linear relationships because they actually imply that there's some kind of a relationship between two things. And also, we're lazy and we don't want to work with, equations that are going to require us to do something like this. So can we find a linear relationship between pressure and volume? And the answer is yes. All right. Volume is over here still. But now we've done 1 over pressure, or an indirect relationship, and we now get this linear line, which makes life lots easier. All right, so basically, here's how this works. If the volume increases, the pressure decreases. All right, or if the volume decreases, the pressure increases, because they are indirectly proportional. Indirectly proportional. Now remember, we're holding in this case N and T are constant. All right, they have some value, but they don't change because they are constant. And so it works out that we have a relationship of pressure times volume is equal to whatever that constant is from the amount and the temperature. Okay. So this is going to be our relationship, okay, indicating that it's indirectly proportional. Okay, so for example, we've got some nitrogen gas. And if I didn't put it here, you ought to be thinking N2 because it's a gas, a nitrogen. And remember, there's those 7 gases or 7 diatomic molecules. So you ought to remember what they are: H2, N2, O2, F2, Cl2. There's also Br2 and I2, but this is a liquid and this is a solid. So these in particular we want to remember for our gas unit, okay, because those are the gases. All right, so we put some nitrogen gas in an automobile airbag, and if we're going to change something now, all right? And so now, if we put it originally at 745 millimeters in a 35-liter bag, then what's the pressure going to be in a 25-liter bag? Now, working these gas laws, it's very important to set this up in a way that helps you identify things, because it's easy to make mistakes. And so you should always set up a table. All right, in this case, we know the pressure of the first one is 745 millimeters of mercury. We also know V1, the first condition, is in 35.0 liters. Now, we're looking for how the pressure changes when we change the volume to 25.0 liters. All right, so you want to set this up because, now this one's not, pressure and volume don't really mix people up too much, but later it will, and it's best to get started on the right foot on these things. Now, because pressure 1 and V1 is equal to some constant, and that's also equal to the same constant for P2, V2, because we didn't change the amount and we didn't change the temperature, these two are going to be equal to each other. And I'm going to rearrange algebraically before I start inputting values. All right, I want to know this P2. All right, so I'm going to do P1 times V1 divided by V2, and that'll give me the second pressure. All right, so now that you've done all this work, all you have to do is, plug and chug at this point. So let me get the right number so I plug and chug correctly here. This would be 745 millimeters of mercury times V1, okay, so 35.0 liters, divided by V2, 25.0 liters. So liters drops out, and I'm going to end up with units in millimeters of mercury. And when I do that, that works out to be 1,040 millimeters of mercury. All right? So that would be the pressure under the new situation. Now, I should do this every time before I start, but I wanted to make a point here. My first thing when I start, I need to think to myself, well, I lowered the pressure from the original container, and so what do I expect? I expect an increase in pressure, right? If the volume is decreased, then I better see some kind of increase in pressure. So now I look here, and sure enough, I have an increase in my pressure here. All right, so you should always take these things and think about them for a minute. If I've got an increase, if I have a decrease in volume, I expect an increase in pressure. All right, so what if I want to know, what if that's not the question? Maybe I ask you, for example, what is the pressure? And notice here I did in atmospheres. Okay, well, this is not the answer. Do you think that answer would be on the exam? Yes, that would be on the exam. But let's finish off this problem. So we want to answer this in atmosphere. So 1040 millimeters of mercury. And I know that's 1 atmosphere over 760 millimeters of mercury is my conversion factor. And this works out to be basically 1.4 atmospheres. What if I want to make your life more difficult, and instead I ask for the pressure in pascals? So instead of being in atmospheres, I ask for this in pascals. I've got to get from a millimeter of mercury to a pascal, and that's not nearly as pretty or easy as this atmosphere business. So in this case, I would have 101,325 pascals for every 760 millimeters of mercury. And so in pascals, the pressure would be 1.4 times 10 to the 5th pascals. All right, so be careful about the units. Gonna have to convert. All right, the second relationship is Charles's law, and that's considering volume and temperature. Okay, and in this case, we're going to hold the pressure and the amount constant. All right, and the way this works out is they are directly proportional. They're directly proportional. And therefore, if the volume increases, I expect the temperature to increase. Or if the volume decreases, I expect the temperature to decrease. So when you're doing Charles's law problems, you should stop and say, what do I expect to happen before I answer the question? So in this case, let's just have a look at this. We've got some kind of a mercury plug here, and this section right here is the gas that's trapped in that tube. All right, so at some particular pressure, temperature, this is 0 degrees Celsius, we have some particular volume. So let's instead consider heating up the water. Notice what's happened to the trapped air. There's a lot more of it now than there was before. Okay, so there is a relationship between the temperature and the pressure, and the volume. Another thing Charles's law tells us is, at least in theory, what the temperature is in terms of Kelvin. Okay, how do we know what Kelvin is? Remember, Kelvin starts at 0 Kelvin. Okay, that's the very least amount of temperature that we can get to. Why? Because if we get to 0 Kelvin, then whatever we are measuring would have a volume of 0. All right, so what happens is we do these experiments that we can tell for sure. Okay, so we're at 0 degrees. We could go colder on some things, but then eventually you have to extrapolate back. And when you extrapolate back, minus 273 degrees Celsius is 0 K. And at that particular temperature, there would be no volume left, okay, in whatever you're doing. Now, that's obviously not possible. If you begin with something that has some volume, you've got to have something in the end that still has some volume. So this is in theory, okay? But we have, or not we, I certainly haven't done this, but very smart people have gotten very, very close to minus 273, where their volume would be 0, okay? They haven't quite got to 0, but I'm not sure that they ever really could in reality. At any rate, the point here is the volume and the temperature are directly proportional. And so, well, this is fine. And so we end up setting up a reaction or an equation that looks like this, where we have V1 over T1 is equal to some constant. And that constant, remember, is where we keep the N and the P constant. Those values still there, but we're not measuring them and nothing has changed. Therefore, V2 over T2 is also going to be equal to that constant. So when we're comparing how things change, we can set up this reaction. V1 over T1 is equal to V2 over T2. And so, let's see. Let's just put in this stuff. You need a table. Don't ever forget your table. So V1 is going to be equal to 25 mils, while T1 is 20 degrees Celsius. V2 is, we don't know. That's what we're looking for. And T2 is equal to 37 degrees Celsius. So what we want is V2, so we'll rearrange. V1, I'm going to multiply T2 out here. That puts that up here, divided by T1, and that's going to give me V2. And so when I calculate up, input all this stuff and calculate all that up, it's equal to 46.3 mils. Okay, so what should I be thinking about? If the temperature goes up, what do I expect the volume to do? I also expect that volume to increase. So I'm feeling pretty good about this answer, right? My volume increased, and so I'm thinking that's really good. Then I go and I try it out on my experiment, and guess what I find? I find that it's only, in the experimental evidence, 26.5 mils. Now, why is this wrong? Okay, that is wrong, and why? Experimentally, I know it's going to be this. Well, the reason is because you have to always, 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 always use Kelvin. Okay, so we're going to add 273 here. That will give us 293 K. All right, and we're going to add 273 here, and that will give us 310 Kelvin, right? Now, when I use these values, I get 25 mils for V1 times T2, which is 310 Kelvin, 310 Kelvin, divided by my Kelvin in T1, 293 Kelvin, and that works out to be 26.5 mils. All right, so Now I'm still happy. I've got a higher volume than I once had, and my experiment and my values work out. And why? I don't care what you're doing in gas laws. Anytime you're thinking about temperature, you better change it to Kelvin. It's always, always, always in Kelvin. Let's see. So what's next? Avogadro's law. Avogadro compared the volume and the amount. Okay, so in this case, we're keeping pressure and temperature constant. All we're thinking about is the volume and the amount, which is in moles. Okay, so N stands for moles here. These turn out to be directly proportional too. And so you end up with a relationship like this, where V1 over N1 is equal to V2 over N2. All right, so let's do a problem. All right, like always, be sure and set up everything so that you can see in a table what you're dealing with. All right, so we have a volume for the first V1 is a 1.5, oops, that's the amount. Okay, so N1 is 1.5 moles, and we know that V1 is 2.5 liters. Now we're going to hold the temperature and pressure constant, and we don't care what that is, it just is being held constant. Then we're going to look for V2 when N2 is equal to 12.0 moles. So before you get started, you've got an increase in moles. What do you expect for the volume? Well, you better see an increase in volume. Okay, increase in volume. So in this case, after we've set all this lovely stuff up, we're going to rearrange. Oh, here, let me put this back up here. We're going to rearrange our constant Avogadro value, and we're going to say, okay, so V1 times N2 divided by N1. So all I did was multiply the N2 across is going to give me V2. So in this case, I'm going to have 2.5 liters from V1. And then it's very important to be sure you get the N2, this thing over here, times 12.0 moles, and divide that all by N1, which was 1.50 moles. And this turns out to be equal to 20 liters. So I actually got the increase that I was expecting. This is what I expected. I went from 2.5 to 20 liters. So I'm pretty happy with that. Now, we know some other things that Avogadro did. You'll remember we already know some of this, okay? What he determined was if we keep the temperature and the pressure constant and all we compare are the volumes and the amounts, okay, he found that no matter what kind of gas you put in here, here's helium, okay, this is helium. It has a molar mass of about 4 grams per mole. Nitrogen, that's N2, has a molar mass of about 28.2 grams per mole. O2 over here is 32 grams per mole. Okay, so that doesn't seem to make any difference here, though. Okay, because no matter whether as long as I have 1 mole of whatever the gas is, the volume at something called STP, which we'll talk about in just a minute, is always 22.4 liters, always. So no matter what I did, this is always 22.4 liters. Another thing we know, and we're going to care about particles later, is that each one of these has 6.022 times 10 to the 23 particles of gas. Okay, whatever that is. It could be H2 or argon or neon or whatever we're talking about. Every single one of these has the same number of particles. All right, now what is STP? That's standard temperature and pressure. Standard temperature and pressure. Standard temperature is 0 degrees Celsius, or 273 Kelvin. Okay, now that's not like the thermodynamics, all right? That was usually performed at 25 degrees, but there wasn't a standard temperature. Here, we actually have a standard temperature, and a standard pressure is 1 atmosphere. Okay, so at standard temperature and pressure, 1 mole of any gas has the same volume always of 22.4 liters. All right, so we will look into more of this later, but I wanted to point out to you that we care about how many and the volume, because this allows us to know lots of things about numbers, particles, and etc. Now, there are other relationships that we haven't really talked about much. All right, we saw Boyle's law and Charles's law. Because the pressure and the volume are related like they are, there can also be a similar relationship as Charles's law, where the pressure over the temperature is held to a constant. There are combined gas laws where we can take the pressure times the volume divided by the temperature, and that gives us some constant. And even if we come down to PV over NT, this also ends up being a constant. So we can, and we'll look at that more a little bit later in ideal gas laws, but we can set up all 4 variables and figure out how something changes, because this is always equal to some constant. Let's see. All right, so this is a little bit more difficult problem. I've got a sample of gas at 500 millimeters of mercury, 25 degrees Celsius, 2 liters. I'm changing it to 1 liter container at 37 degrees, and I want to know what's the new pressure. This is starting to get pretty hairy, okay? So first, I'm going to set up my table. So my pressure 1 is 500 millimeters of mercury. My volume 1 is 2 liters. My T1 is 25 degrees Celsius. P2 is what I'm looking for, I don't know. V2, let's put these all in the same way. V2 is now equal to 1 liter, and T2 is now equal to 37 degrees Celsius. Now, can I just look at this and make a decision? Probably not very well. In this case, the volume decreases, so I might expect the pressure to increase. But here, the temperature increases, and so I would also expect the pressure to increase. So I'm really not sure how to think that through. I better calculate it. Now, what's the first thing you should always do? This has got to be in Kelvin. So this is 298 Kelvin, and this is 310 Kelvin. All right, if it's in degrees Celsius, hey, it'll be on the exam, that answer, but that's not right. All right, so let's see what I do with that problem. All right, so I'm going to rearrange algebraically. Let me put up the first equation. This is P1 times V1 divided by T1. Now, I could put N1 in here, but I don't really have anything. It's still the same amount every time. That's going to be equal to P2 times V2 over N2 times T2. But, as I just said, nothing about the amount changed, so I don't really need to deal with that. I can leave that one off. Then, I can rearrange this, and what I want all by itself here is the pressure. All right, so what I'm going to do is I'm going to multiply T2 across and divide V1 across. This works out to be P1 V1 times T2 divided by T1 V2, that's equal to P2. So you see, it's very important to be organized, because even if you get this far, if you don't have this table, you'll end up putting the temperatures in the wrong place or the volumes in the wrong place. You'll end up making a mistake. So make this table. All right, so now let's input our values. All right, we know that P1 is 500 millimeters of mercury. We know that V1 is 2 liters. And we know that T2, way over here, is 310 Kelvin. We're going to divide that now by T1. T1 is 298 Kelvin. And V2, which is 1 liter. Now let's look just for fun at our units. Liters drop out, Kelvin drops out, and I have some millimeters of mercury as an answer, which makes me happy. And didn't really notice this before, but this works out to be what our last answer was. I don't know that I like that. 1040 millimeters of mercury. I'm going to just check with my calculator, or not. All right, well, I hope this is correct. I'm kind of weirded out because it's the same answer as the one we got on the last one, so that kind of has me worried. But hopefully I have good sense. Now I want to do one more. No, actually, I think I'll just let you get those in your homework and in your assignments. Practice, practice, practice. Write that table. Remember the Kelvin degrees. After you get the table, do the algebraic rearrangement of these equations and these relationships to each other. It can get pretty hairy, and you can make silly mistakes if you don't have this lovely table. Okay. And if you don't do this algebra. So take your time and find out how to set these up properly.